This pulsing microchip represents the Grace Blackwell GB10 superchip inside the NVIDIA DGX Spark, providing 1 petaflop of computing power and 128 gigabytes of memory in a desktop unit. But when you attempt to schedule this hardware through standard Kubernetes, the device plugin crashes, throwing a memory error and stopping the deployment process. This side-by-side diagram shows the cause. On the left is standard architecture, where the GPU has separate dedicated VRAM. On the right is the GP10's unified memory architecture, where the CPU and GPU share a single memory pool. The classic Kubernetes device plugin is programmed to look for discrete VRAM. When it queries the shared pool, the hardware responds with a not supported error, and the plugin shuts itself down. By updating the device plugin to handle this memory mismatch, we can schedule the hardware properly. This quick fix allows a massive live large language model to run entirely on your local desk in under 6 minutes. Step 1 is confirming the GPU works on the host. Open your terminal and run the standard NVIDIA SMI command to check the baseline metrics. This terminal readout shows the diagnostic results. Notice the row reporting memory usage as not supported. Because this is a unified memory chip without a dedicated frame buffer, this is expected behavior, not a hardware defect. Next, we need to register the NVIDIA runtime so it survives system restarts. You do this by appending the runtime configuration directly into the container dconfig pile. We then execute a single-line curl script to install K3s. This provides a lightweight Kubernetes orchestrator suited for an ARM64 node. Run kubectl get nodes to verify the installation. Once the node reports a ready status, the cluster is live. With the correct runtime designated and the cluster active, we have the foundation required to apply the specialized GPU fixes. Step 2 targets the device plugin. We resolve the unified memory crash by installing the NVIDIA GPU Operator. The requirement here is to use a device plugin version of 0.17.4 or higher. This release contains the logic required to accept the not supported memory response and successfully register the hardware. The DGX operating system already includes pre-installed drivers and the container toolkit. If the operator tries to install its own versions over them, the setup will fail. This terminal mockup shows the Helm installation command. We specifically set driver.enabled equals false and toolkit.enabled equals false, ensuring the operator only manages the fixed plugin. Check the node capacity metrics. When the system successfully advertises one schedulable NVIDIA GPU, the memory issue is resolved. The DGX Spark contains one physical GPU. To allow multiple AI pods to utilize it concurrently, we enable time slicing. We apply a config map to the cluster, instructing Kubernetes to advertise 4 virtual GPU replicas from that single unit. By deploying the correct plugin version and dividing the hardware temporally, a single desktop chip operates as a multi-tenant AI cluster, handling separate workloads simultaneously. Now that the infrastructure is configured, we test the system by deploying an AI workload to one of our virtual GPUs. We apply a deployment manifest configured to download and serve the Qwen 3 language model using vLLM. Check the pod logs to watch the initialization. You need to confirm the model weights successfully load directly into the shared memory pool. This split-screen terminal shows the active environment. With the initialization complete, we send an OpenAI-compatible API request directly to the running pod. The streaming text response from the model confirms it is processing tokens on a time-sliced GPU without encountering memory access errors. Generating this response proves the abstraction layer is functional. The complexity of the unified memory architecture is now handled by the plugin, hidden from the end developer. This diagram maps out the complete stack. We have our lightweight orchestrator as the foundation, the patched hardware operator managing the shared memory in the middle, and our active language model running on top. By strictly controlling these 3 software layers, we have enabled a data center-grade AI stack to run on a local desktop superchip. For advanced observability, you can optionally configure the DCGM exporter to point at the host engine. This enables live terminal monitoring of GPU performance metrics. Correcting the unified memory configuration ensures that high-performance local hardware works with standard cloud-native deployment practices.